Bam! Mr. True, in this video I would like to re-emphasize why you care where the tangent lines are horizontal. And you're going to find out where the tangent line or the slope of your function, here we have a sort of weird looking function f, I've just sketched off a line. Why do we care about where its slope is equal to 0? Why do we care about where the tangent lines are equal to 0? Well, I've marked off 3 points here, or in this graph I've marked off 3 points. One here at value C, one here at value B, and one here at the x-coordinate of A. We care about where the slope is equal to 0. We care about where the slope of the tangent lines are equal to 0 because we can then analyze the derivative to the left and the right of those values of x where the graph has a slope of 0 to see if we found a relative minimum or maximum. If to the left of this value where the slope is equal to 0, if to the left of that your first derivative is negative and to the right your first derivative is positive, well then your graph was falling with the negative slope and then bottomed out and then started to rise with a positive slope. That's a relative minimum. Or to the left of your particular value that you find a slope of 0 where the tangent line is horizontal, if the derivative is positive to the left and negative to the right, you found a relative maximum. And then, just because you find a place where the tangent line is equal to, has a slope of 0, or the slope of the curve is equal to 0, you have not automatically found a relative max or min. Most of the time you will have, but not all the time. In this case, I have a graph that is falling, so my first derivative will be negative. Then it just sort of flattens out for a second, and then just happens to start to fall again. So that means that we can find places in our functions where the derivative is equal to 0, but yet we have not found a relative min or max. So we're just going to do 2 examples. I got one with just a normal polynomial. I got another one with trig functions and a little bit of use of chain rule. We're going to find out where those derivatives are equal to 0, and that's all we're going to do at that point. But again, once you find out where those derivatives are equal to 0, you can plug in a number into the derivative, just a little bit less, and then a little bit higher, and look for those sign changes if they do indeed exist. Again, negative on the left, positive on the right, relative min. Positive on the left, negative on the right of this particular x value where the slope is equal to 0, relative max. No sign change, whether it's going down on both sides or up. No sign change means as well, not a relative max or min. Let's see what those examples look like. Woo! Well, here's our first example. We have f of x is equal to x cubed minus 4x squared plus x plus 6. So we're going to find the derivative. So f prime of x is equal to, we're going to apply the power rule here and get 3x squared. We have a constant of power, so we're going to bring that down. 2 times negative 4 is negative 8. Bring that exponent down from 2 to 1. Here we have plus x, so that's just going to be 1. And the constant is going to be 0. So the derivative is 3x squared minus 8x plus 1. So this is the derivative. This will tell us the slope of this function at any point where x is defined. So we are going to solve for what? We want the derivative to be 0. That is when the tangent lines are horizontal. So we're going to let f of x equal 0. 3x squared minus 8x plus 1. And see if we can factor this, because that'll take a little bit less work. We're going to take the first and last term, multiply those together, get 3, and then look at that product and go, is there a way I can factor 3, the product of the leading coefficient and the constant? Are there factors of 3 that are also going to add up to be negative 8? And the answer to that is no. So this trinomial, this quadratic, is not factorable. So that means that we're going to, since it is a quadratic, solve it using the quadratic formula. That is, in case you did forget, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And of course we know that we want, the equation set equal to 0. We want all of the terms here, we want the exponents counting down. And we have a is equal to 3. B is equal to negative 8, and C is equal to 1. So, doing our substitution, we have x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. I do like to use the parentheses and kind of lay it out before I even start plugging the numbers in. That way, if I'm plugging in a negative, I'll know that there was a negative from the formula and a negative from the values that I'm plugging in. Like here our b is negative 8. So it's the opposite of negative 8 plus or minus square root negative 8 squared minus 4a, which is 3. 4ac, c is 1 all over 2a. So all we have to do is, work this out, and I'm not going to worry about trying to check to the left and right to see if it's a relative max or min. I'll leave it up to you if the problems you're doing requires that. We're just going to find the x values at which the derivative is equal to 0. So we have x is equal to positive 8 plus or minus the square root. Negative 8 squared is 64. Negative 12 from negative 4 times 3. That's a little bit long now. All over 2 times 3, which is equal to 6. 64 minus 12, that's going to be 64. Now it's 54 and 52. So we have 8 plus or minus the square root of 52 over 6. Now, I want to leave this in exact form, and I want to see, is there a way to reduce the square root of 52? I'm looking for a perfect square in 52, like 4, 9, 16. 5 squared is 25. I'm pretty sure from my notes that the biggest perfect square in here is 4, and that's it. Let me see. Yes. So we're going to rewrite this as 8 plus or minus the square root of 4 times 13, right? 4 times 10 is 40, and 4 times 3 is 12. 40 and 12 make 52 over 6. Yeah, you don't have to, but it is nice to leave the perfect square first all the time because that's going to come out. The square root of 4 is equal to 2. So we have, we're showing all these steps, 8 plus or minus 2 square root of 13 all over 6. And of course 6 is even, 8 is even, 2 is even. All three of these terms have an even or a factor of 2. They're all even. If there was a 1 there and it was just the 8 and the 6 which were even, nothing would reduce. But we can factor a 2 out of here. Factor 2 out of the 6, cancel those 2's out, and boom, there's your answer. 4 plus or minus square root of 13 over 3. Double check my notes here. Yes, it is. One more example, it will involve trig functions. Woo! For our last example, we have f of x is equal to 2 sine x plus cosine of 2x. So we want to find the derivative. So that means that we're going to have f prime of x, or the derivative of f of x, is equal to 2. Now the derivative of sine is cosine, so we have 2 cosine x plus, we have the cosine of 2x. Now here I could just write cosine of x and be done finding the derivative of sine. But again, we have this inside function u is equal to 2x. So we're going to find the derivative of cosine. Now the derivative of cosine, shouldn't be writing these symbols, these sign symbols, just automatically, just assuming you know what it's going to be. So let's take that out. The derivative of cosine is negative sine. So minus sine of 2x. But now I have to take care of the derivative of the inside function. So this is the derivative of the cosine function times the derivative of the inside function. And the derivative of 2x is equal to 2. So we have, well, there's not really much to clean up. We have just, 2 times cosine of x. If I want to take the 2 out of both of these terms, minus the sine of 2x equals f prime of x. We are looking for where, again, the tangent lines are horizontal. We were looking for where the derivative is equal to 0. So we're going to take out this f prime of x and replace it with 0 to find those horizontal places, the x values where those tangent lines are horizontal. Well, now I can take both sides and divide it by 2, which is just going to cancel that out, and this is going to remain 0. Now I've got 0 equals cosine of x minus sine 2x. Remember solving equations involving trig functions back in either trigonometry or pre-calculus? You cannot solve for an equation that has two different trig functions in it because it acts as two separate variables. It's like having an equation with an x and a y in it. And even if they were the same trig function, you have a single angle and a double angle. That is also a problem. That is also going to act as if there were two separate variables. So normally when you have one equation and two variables, you cannot solve for those two variables unless they factor apart. So that's what's going to happen here. We have 0 is equal to cosine x minus, now, all those identities you learned in trig and pre-calculus, those 3 chapters in pre-calc where it wasn't just a bunch of algebra review. All those identities are still coming back and are still going to get used in calculus. I need to get this double angle to come down to a single angle of x. And the cosine, or excuse me, the sine of 2x is equal to 2 sine x cosine x. Now each of my terms, now I have one angle. They're all single angles now, so that's not an issue. But again, I still have those two different trig functions, so I still basically have two variables in a single equation, and that is usually a problem, except here I have the cosine function in each of my two terms. If I factor that out, if I divide it out of those two terms, I get 0 is equal to cosine of x. Now cosine of x divided by cosine of x is equal to 1, and 2 sine cosine of x divided by cosine of x is going to leave me with sine x. So my two different variables, my two different trig functions are in, there's only one in the first factor, there's only one in the second factor. What do you do after you factor? You set each factor equal to 0 because one of these has to be 0 for the equation to be equal to 0. And when I do that, cosine of x equals 0 and 1 minus 2 sine x equals 0. Well, now I have equations that only have one variable in each one of them. X here is going to be equal to the inverse cosine of 0. And where on the unit circle, we're just looking for answers within one rotation, 0 to 2 pi. Where is cosine equal to 0? Well, cosine on the unit circle again is x over r, and on the unit circle, because r is 1, it's just x. So where on the unit circle is the x value is equal to 0? What rotation, that's what you get out of an inverse trig function, what rotation will give you a cosine value of 0? Well, that's at 0 radians, that cosine value is 1. It's at pi over 2, pi, 3 pi over 2. So we have pi over 2 and 3 pi over 2. And then we have, I feel like I made a mistake somewhere. Yes, only in my notes. Good thing I'm redoing this again. Sorry for the interruption. So here we have 1 minus 2 sine x. So we're going to bring the 1 over and get negative 2 sine x equals negative 1. Divide both sides by negative 2, and sine x is equal to 1/2. Now you need to get the sine function away from x. So x is going to be equal to the inverse sine of 1/2. Now on the unit circle, sine is y over r. Sine of theta is y over r. And on the unit circle, again, we're just looking for the y values. So what rotations on the unit circle have a y value of equal to 1/2? That's going to be 30 degrees, or pi over 6, and 5 pi over 6. So x is equal to pi over 6, 5 pi over 6. I'm going to go make my little sign error correction, or correct my sign error on my notes while you go do your homework. I'm Mr. Taru. Go do your homework.